Quantum numbers describe values of conserved quantities in the dynamics of a quantum system. In the case of quantum numbers of electrons, they can be defined as the sets of numerical values which give acceptable solutions to the Schrödinger wave equation for the hydrogen atom. Perhaps the most important aspect of quantum mechanics is the quantization of observable quantities. Since quantum numbers are discrete sets of integers or half-integers, although they could approach infinity in some cases, this is distinguished from classical mechanics where the values can range continuously. Quantum numbers often describe specifically the energy levels of electrons in atoms, but other possibilities include angular momentum, spin, etc. Any quantum system can have one or more quantum numbers. It is thus difficult to list all possible quantum numbers. How many quantum numbers? The question of how many quantum numbers are needed to describe any given system has no universal answer. Hence, for each system one must find the answer for a full analysis of the system. A quantized system requires at least one quantum number. The dynamics of any quantum system are described by a quantum Hamiltonian. There is one quantum number of the system corresponding to the energy, i.e., the eigenvalue of the Hamiltonian. There is also one quantum number for each operator O that commutes with the Hamiltonian. These are all the quantum numbers that the system can have. Note that the operators O defining the quantum numbers should be independent of each other. Often, there is more than one way to choose a set of independent operators. Consequently, in different situations, different sets of quantum numbers may be used for the description of the same system. Spatial and angular momentum numbers. There are 4 quantum numbers which can describe an electron in an atom completely. Principal quantum number, Azimuthal quantum number, magnetic quantum number, spin quantum number. Traditional nomenclatures. Many different models have been proposed throughout the history of quantum mechanics, but the most prominent system of nomenclature spawned from the Hund-Mulliken molecular orbital theory of Friedrich Hund, Robert S. Mulliken, and contributions from Schrödinger, Slater, and John Leonard Jones. This system of nomenclature incorporated Bohr energy levels, Hund-Mulliken orbital theory, and observations on electron spin based on spectroscopy and Hund's rules. This model describes electrons using 4 quantum numbers, n, m, as given below. It is also the common nomenclature in the classical description of nuclear particle states. Molecular orbitals require different quantum numbers, because the Hamiltonian and its symmetries are quite different. The principal quantum number describes the electron shell, or energy level, of an atom. The value of n ranges from 1 to the shell containing the outermost electron of that atom, i.e., n equals 1, 2. For example, in cesium, the outermost valence electron is in the shell with energy level 6. So an electron in cesium could have an n value from 1 to 6. For particles in a time-independent potential, it also labels the nth eigenvalue of Hamiltonian, i.e., the energy, E, with the contribution due to angular momentum left out. This number therefore has a dependence only on the distance between the electron and the nucleus. The average distance increases with n, and hence quantum states with different principal quantum numbers are said to belong to different shells. The azimuthal quantum number describes the subshell, and gives the magnitude of the orbital angular momentum through the relation L2 equals H2. In chemistry and spectroscopy, equals 0 is called an s orbital, equals 1, a p orbital, equals 2, a d orbital, and equals 3, an f orbital. The value of ranges from 0 to n-1, because the first p orbital appears in the second electron shell. The first d orbital appears in the third shell, and so on. Equals 0, 1, 2, n-1. A quantum number beginning in 3, 0, describes an electron in the s orbital of the third electron shell of an atom. In chemistry, this quantum number is very important, since it specifies the shape of an atomic orbital and strongly influences chemical bonds and bond angles. The magnetic quantum number describes the specific orbital within that subshell, and yields the projection of the orbital angular momentum along a specified axis. Lz equals mh. The values of m range from -2, with integer steps between m. The s subshell contains only one orbital, and therefore the m of an electron in an s orbital will always be 0. The p subshell contains 3 orbitals, so the m of an electron in a p orbital will be -1, 0, or 1. The d subshell contains 5 orbitals, with m values of -2, -1, 0, 1, and 2. The spin projection quantum number describes the spin of the electron within that orbital, and gives the projection of the spin angular momentum s along the specified axis. Sz equals ms(h). In general, the values of ms range from -s to s, where s is the spin quantum number, an intrinsic property of particles. Ms equals -s, -s plus 1, -s plus 2, s minus 2, s minus 1. An electron has spin number s equals 1/2. Consequently, ms will be plus or minus 1/2, referring to spin up and spin down states. Each electron in any individual orbital must have different quantum numbers because of the Pauli exclusion principle. Therefore, an orbital never contains more than 2 electrons. Note that there is no universal fixed value for m and ms values. Rather, the m and ms values are random. The only requirement is that the naming schematic used within a particular set of calculations or descriptions must be consistent. These rules are summarized as follows. Example: the quantum numbers used to refer to the outermost valence electrons of the carbon atom, which are located in the 2p atomic orbital, are n equals 2, equals 1, m equals 1, 0 or -1, ms equals 1/2. Results from spectroscopy indicated that up to 2 electrons can occupy a single orbital. However, 2 electrons can never have the same exact quantum state nor the same set of quantum numbers according to Hund's rules, which addresses the Pauli exclusion principle. A fourth quantum number with 2 possible values was added as an ad hoc assumption to resolve the conflict. This supposition could later be explained in detail by relativistic quantum mechanics and from the results of the renowned Stern-Gerlach experiment. Total angular momenta numbers. Total momentum of a particle when one takes the spin-orbit interaction into consideration. The L and S operators no longer commute with the Hamiltonian, and their eigenvalues therefore change over time. Thus another set of quantum numbers should be used. This set includes the total angular momentum quantum number, J equals plus or minus S, which gives the total angular momentum through the relation J2 equals H2J. The projection of the total angular momentum along a specified axis, Mj equals minus J plus 1, minus J plus 2, J minus 2, J minus 1, J analogous to the above, and satisfies Mj equals M plus ms and M plus ms J. Parity. This is the eigenvalue under reflection, and is positive for states which came from even and negative for states which came from odd. The former is also known as even parity and the latter as odd parity, and is given by p equals. For example, consider the following 8 states, defined by their quantum numbers. The quantum states in the system can be described as linear combination of these 8 states. However, in the presence of spin-orbit interaction, if one wants to describe the same system by 8 states which are eigenvectors of the Hamiltonian, we should consider the following 8 states. Nuclear angular momentum quantum numbers in nuclei. The entire assembly of protons and neutrons has a resultant angular momentum due to the angular momenta of each nucleon, usually denoted I. If the total angular momentum of a neutron is Jn equals plus s and for a proton is Jp equals plus s, then the nuclear angular momentum quantum numbers I are given by I equals Jn minus Jp, Jn minus Jp, plus 1, Jn minus Jp, say p plus 2, minus 2, minus 1. Parity with the number I is used to label nuclear angular momentum states. Examples for some isotopes of hydrogen, carbon, and sodium are the reason for the unusual fluctuations in I, even by differences of just one nucleon, are due to the odd, even numbers of protons and neutrons. Pairs of nucleons have a total angular momentum of 0, leaving an odd, even numbers of unpaired nucleons. The property of nuclear spin is an important factor for the operation of NMR spectroscopy in organic chemistry, and MRI in nuclear medicine. Due to the nuclear magnetic moment interacting with an external magnetic field, elementary particles contain many quantum numbers which are usually said to be intrinsic to them. However, it should be understood that the elementary particles are quantum states of the standard model of particle physics, and hence the quantum numbers of these particles bear the same relation to the Hamiltonian of this model as the quantum numbers of the Bohr atom does to its Hamiltonian. In other words, each quantum number denotes a symmetry of the problem. It is more useful in quantum field theory to distinguish between spacetime and internal symmetries. Typical quantum numbers related to space-time symmetries are spin, the parity, C parity and T parity. Typical internal symmetries are lepton number and baryon number or the electric charge. A minor but often confusing point is as follows. Most conserved quantum numbers are additive, so in an elementary particle reaction, the sum of the quantum numbers should be the same before and after the reaction. However, some, usually called a parity, are multiplicative, i.e., the product is conserved. All multiplicative quantum numbers belong to a symmetry in which applying the symmetry transformation twice is equivalent to doing nothing. These are all examples of an abstract group, called Z2.